Okay, good morning, everyone, and welcome to the first press briefing at LPSC this year. My name is Suraya Faruqi, and I'm the Director of Communications at University Space Research Association in Columbia, Maryland, and I'm the press officer for LPSC, supporting the press activities here. So the format of today's briefing is basically 15 minutes for the speaker, lead speaker, and followed by about 5 minutes by the second speaker. And please hold your questions till after the speakers have finished their presentation. The first speaker today is the lead author on the paper that was just published in Science. The embargo was lifted at 9:30 a.m. this morning, so the results are literally hot off the press. Dr. El-Maarry and Dr. Pajola will talk about the remarkable changes that have occurred on the surface of Comet 67P after its perihelion passage. But before I turn it over to Dr. El-Maarry, I just want to give you a brief introduction of the two speakers. Dr. El-Maarry is currently a visiting scientist at the Laboratory for Atmospheric and Space Physics at the University of Colorado in Boulder. Prior to that, he was a postdoc at the University of Bern in Switzerland. He earned his PhD from the University of Göttingen in Germany under a Max Planck Fellowship. Dr. El-Maarry is an active member on a number of space missions instruments that include OSIRIS, Camera Onboard Rosetta, HiRISE on Mars Reconnaissance Orbiter, and he's the co-investigator for CASIS Camera Onboard, the ExoMars Trace Gas Orbiter. His research interests are diverse, but focus on surface geomorphology and processes, particularly fractures on planetary bodies. Dr. Maurizio Pajola is currently at NASA Ames Research Center. His main interests at Ames is in mineralogical studies of the surface of the Martian satellite Phobos. And as a postdoc, his studies focused on the Rosetta data of Comet 67P, specifically on Boulder's analysis and surface geomorphology. He did his PhD research at the NASA Jet Propulsion Lab and at the Space Center of the University of Padova in Italy, focusing on Mars ancient paleohydrology. He's a lead proposer of Mars rover landing sites, both for ESA and NASA, Phobos, Mercury, and small body spectrophotometry, and Boulder studies, both on small bodies, such as asteroids and comets, and Mars. So without any further ado, I'd like to introduce now Dr. El-Maarry.
Thank you very much, Suraya. Good morning, everyone. Thank you for being here. It's a real pleasure to report on these results for the first time here at LPSC. This study really is about all the significant surface changes we've seen on Comet 67P. It's really significant because that's actually the first mission that we've been able to have such a huge data set of high-resolution images, but at the same time also having a longevity, a long mission where we were able to look at a comet, study it, how it would evolve through more than 2 years as it journeyed through the inner solar system. So without further ado, we go now. But before starting with Rosetta, let's take a look very quickly at what we had before Rosetta. So basically, we had a few images from a number of comets or numerous missions. These were actually excellent data sets at the time. We've learned a lot from these. But in terms of changes, the only comet that we actually had an idea of change on it was Comet Tempel 1, because it was and remains to be the only comet that has been visited by 2 different spacecraft at different times. So that's the only place where we were able to look at images, see, what has changed in that time frame. And in this case, we have Comet Tempel 1 in 2005 that was visited with Deep Impact mission, and then Stardust next in its next perihelion passage. Because this is a comet that again has very similar orbital period like Comet 67P. And they've seen a few changes, but one of the most significant ones was what we call scarp retreat, where the edge of this material is just retreating backwards through erosion. And you can see it here on Comet Tempel 1, right there at sort of the middle of the comet. And there's been a retreat of material by around 50 meters. Basically, that's the best thing we've had. We had limited information on what other changes might happen on a comet. when do they actually start or kick in, and how long are they there, how long are these activities going on. Also, rates of change is something that we didn't have any information about before Rosetta. So as a sort of a refreshing timeline of important dates, Comet 67P was encountered by Rosetta in August 2014. We had the landing of Philae, which was a pretty historic event in November. And then we had perihelion time, which is a very significant time because this is the time when the comet is very close to the sun, and this is where you get maximum activity, and this would be the time to have the maximum amount of change. So basically what I'm going to show you today is images from before perihelion, when the comet was rather dormant, relatively speaking, and then you get all the activity, you get things like that happening, and we look at images post-perihelion and see what changes we have. So we actually have a broad range of changes. The first one I want to highlight is cliff collapses. So we didn't only see one, but we've seen a number of cliff collapses. There's always going to be a map there with regional, with names of regions, so you also have an idea of where the change is taking place. We've seen a number of cliff collapses. This is one of the most notable events, and I'm not going to speak a lot about this. I'll leave this to my co-author on that paper and the lead author on the Nature Astronomy paper specifically on that event because it's really significant. So I'm going to move on. Another feature that we've seen, there was a large fracture at the neck that we've encountered when we first had the first images of the comet. It's running here around Aniket region, also maybe possibly extending below the dust in Happy. And we can see almost 500 meters length scale of that fracture. And after post-perihelion images, we've noticed that this fracture has actually evolved and has increased in length by around 30 to 40 meters at its tip here. And we've also had a development of a new fracture there, almost 150 meters in length. Now, the timing, and this is really what's special about Rosetta, we have a lot of images, we can constrain when changes take place, and the timing of when the fracture evolved seems to coincide rather well with the time when the comet actually sped up around perihelion. So when you get a lot of activity, this is a very small body, it's really small to the point that these jets are going to introduce some torques, some forces on the comet affecting its rotation. So what happens is that the comet actually speeds up due to this activity around perihelion, and when it speeds up, models have shown that you're going to introduce stresses into that body as it rotates, which tends to concentrate in the neck region. So these stresses would lead to development of new fractures or evolution of pre-existing ones. And there have been models that have suggested this, and now we have a visual confirmation of this. So in a sense, the comet probably is eventually going to split up as it's going to speed up more and more, and we have evidence of that. But when is that exactly going to happen? We, of course, have no idea. Another interesting feature we had is this large boulder we have in an area called the Honsu region, and you can see it here in pre-perihelion images, and then you can see that it has moved here for around 150 meters. So in American terms, more than a football field length. This is a really large boulder. It's around 30 meters in size. And so what you have here is actually a rock from the moon with Harrison Schmitt there. This is sort of a 30-meter-ish boulder. So just get an idea of the magnitude of that boulder that actually moved on the comet. And when you put in, you plug in the numbers, because we can see this boulder from all the sides, we can get its volume, we can measure its volume. Using the density of the comet as the bulk density as an estimate, we can get an idea of how heavy it is, its mass. When you factor in, of course, the very low gravity of the comet, it still amounts to the same force. So now we're going to think in Earth terms. So the same amount of force you would need to lift a boulder that is 250 kilograms heavy. The amount of force is exactly the amount that you would need to move that boulder on a comet, so which has very low density, very fragile. Something that would be a little bit non-intuitive. But in fact, we calculated that a strong outburst or jet activity should in principle be able to lift the boulder or at least move it. And indeed, this is an area where we've seen a lot of massive outburst events, very localized. You have this one here, for instance. This is another one that actually happened after the boulder has moved, because you can see the boulder here. This is an image taken 1 hour before that. And you can see that there is another localized jet right over there. So we think that activity is a key role here in moving this boulder. We move into a second category, and this is where we actually have things that are moving and being transported away or being deposited, what we would call in geological terms erosion. And one of the most significant examples we have is in this Imhotep region, one of these equatorial parts of the comet. There's a layer of dust here, significant amount of smooth materials, and you can see here in this image that this material has been chucked away, removed, and we've exposed a bunch of new circular features. There's a very interesting boulder here we have in red arrow. You can see it's partially exposed in that image. This is a really cool boulder because we can use it actually to sort of measure. We can just measure the height of that boulder now through high resolution images, and we're able to estimate how much actually material got removed in this location. And definitely you have more than 3 meters of material in terms of vertical erosion occurring here. We've removed a lot of material in this area, in this highly localized place. Then we move to transient changes, and by transient I mean things that developed at some point. We have patterns that would grow in smooth materials, and with time they would actually fade away or completely disappear, and that's why we just call them transient changes. And this is one of the prime examples. In the happy region in the neck, we have all these smooth materials there. You develop sort of a feature there, pitted-like structure in January 2015. That's actually way before perihelion. And by June, this material has completely disappeared. This pattern has entirely disappeared, almost reverting to how it looked like earlier. Anubis is one of the other locations where we've seen something like that. So let's focus on this. We have this depression here. You can see this rim of this depression. You have a boulder one there, it's outside. And when you look at post-perihelion images, you can see that this depression has enlarged substantially in size, and the boulder now is sitting inside. Now, a really cool thing about this location is that we have actually a lot of images, and we can constrain when the erosion took place and how fast it was. And by looking at these images, we see that we were getting rates of around a few meters per day at maximum time of activity around perihelion. We also see that the activity is accompanied with brightening of the surface, as you can see here. And even notice here in August, this depression has not still grown substantially, but there's brightening of the rim there. And when we look at spectrophotometric analysis, we analyze this with a number of filters that the OSIRIS camera has. We get an idea of this material that is much brighter than the comet, and that is very consistent in its spectral behavior with exposed water ice rather than frost. So this is ice that is being exposed, it sublimates away and drives the erosion and creation of these large depressions. And you can see here that this material has enlarged in size indeed, this depression, by more than 50 meters and a few meters deep. So again, you're looking at features that are, in that case, it didn't disappear, but it stopped at some point after we've gone past perihelion. Another location I want to highlight are these beautiful ripples we had. It was really such a special feature. We liked it so much when we saw it in the first images, because this is one of the isolated features. It looks to be confined to this location in the happy region, and now we can call them recurrent ripples. Because when we look at images in April 2015, for example, these features had disappeared in a sense. We started growing up these circular features, developing new ones. You can see others here as well. And by July 2015, we had this large circular feature there that's around 100 meters in diameter. And again, notice how you have this brightening of the rim there. So again, this is seems to be a common mechanism by which you're modifying the surface of the comet and losing material. And when you look at this December 2015 image, you see you have some remnants of that circular feature. You've deposited apparently new materials, and you've created again new features, new recurrent ripples, exactly at the same location. So these pesky features just don't want to go away, and they seem to be intent on appearing on the comet at exactly the same location. Now, if we just put in all these events together, stack them because we want to compare, we want to correlate this to the distance to the sun, the heliocentric distance, and see the effective season. So we correlate that with the subsolar latitude at the time the event took place. And we'll see that most of the changes are starting at 3 astronomical units. They are actually in full swing at around 2 astronomical units, where you see a lot of these events here. Mostly all the stuff that you see here, all these events in blue, are events that are following the subsolar latitude, and that means they need the sunlight to engage the activity itself, to motivate it. So you get a lot of sunlight, you get a lot of heat, you drive sublimation, and that's why most of these events appear to be insolation-driven, as we call them. Some of these events do not follow this trend, and we think we have really good reasons for this. So for instance, this one here is the fracture, and this is indirectly linked to the activity. It has to do more with the spinning of the comet, and that is why it's not consistent so much with the subsolar latitude. The cliffs here, for instance, have this geometry, so it has nothing to do with the sun falling directly on the cliff. You actually want the activity to occur when the sun is shining on the head on the wall of the cliff itself. So again, it doesn't coincide with subsolar latitude, but falls in at the time we infer to have maximum insolation. So in summary, we've seen a lot of changes. However, they seem to be localized in certain locations. So these circular features occur in certain locations in the smooth plains, not everywhere. We've seen this area where we had a big chunk of material being removed. Again, it's localized. And that's telling us that we have some sort of lateral heterogeneity at the surface. It's not the same everywhere. We see that most of the activities are on perihelion, generally following periods of increased activity. However, the key thing here, and sometimes negative results can in a sense be positive and drive research forward, because we didn't get fireworks and comets splitting and things breaking up and massive depressions being created. So we didn't see major changes in the comet's landscape. And in that sense, I don't mean the duck shape itself, because this has to do with the merging of the lobes, which happened a long time ago. What I'm talking about in terms of landforms are these major cliffs that are hundreds of meters in size, like Hathor, these large-scale depressions. We didn't see any massive outbursts that actually sculpted the surface, created large depressions and so on, or massive cliff collapses. We've seen cliff collapses, but nothing that has changed the landscape of the comet. So that is telling us something. Apparently it means that we had much more activity earlier in the comet's lifetime. When we look at Earth-based observation we have for Comet 67P, we can see that most of these activities in this cycle appears to be consistent with the previous cycles, at least back to the 1980s, but we have little information about what happened when it just entered the inner solar system in the 1950s. So perhaps this is the time for comets, just when they enter the inner solar system, when the real fireworks kick in. And the fact is, it's possible that also it may have had activity early on, but if that was the case, then that would mean that we also had chemical evolution of the comet with time, and that maybe we had higher inventory of CO or CO2 ices in the past, or even amorphous ices, because these sort of ices will become active at a much lower temperature, which means also at a larger distance. So I'm going to stop here with this, and I'll give the mic, so to speak, to Maurizio, as he speaks a little bit more about the cliff collapse, which is a really significant event.
Okay, thank you so much, Rami, and thanks LPSC for giving us this possibility. So what I'm showing you here is one of the most dramatic change that we have observed on the surface of 67P, and I would like to thank all the co-authors and the entire Rosetta team, the Osiris team, and also ESA for giving us this great opportunity to analyze these images. So, as you have seen, thanks to Rami's presentation, this is Comet 67P, and one of the most interesting area that I was analyzing is this one right here. This is called the Aswan region of 67P, and it's basically located on the Set region, which is this area right here. So the biggest niche that we have here, and the biggest plateau that we have is this right here, and close to the edge of the cliff right here, we could observe a fracture, a pretty big fracture. We are talking about a width of 2 to 3 meters and length of 70 meters. So it's a pretty impressive thing. At the time when I was analyzing the images, we were basically betting and hoping that it was collapsing down during the lifetime of Rosetta, but it was not obvious at all. So all the images that you are looking here, they are of September 2014. Then, Okay, so this is just an image. We are basically seeing face on the cliff right here, and this is an illuminated area. Then on 10 July 2015, what we had the chance was to observe, thanks to the, not the OSIRIS instrument, but the NAVCAM, the navigation camera on board the Rosetta spacecraft. We had this incredible luck to observe an outburst. And this outburst, which is right here, you can really see the other activity that is surrounding the comet with the subsolar point. But in the night side, we can really see this pretty wide outburst. So at that time, one of the co-authors, Jean-Baptiste Vincent, had the possibility to compute and analyze basically the area that it was departing of. And it was exactly the Aswan cliff and the Aswan area. So here is an image of December 2015, so which is a result of this possible outburst. We can really see a bright feature that is appearing right here. So consider that this is an image of December 2015, where basically I was detecting this surface change. It was in January 2016. But then we were like Sherlock Holmes. We were trying to go back in time and trying to see when was really this cliff collapsing. So that's why we were going back in time, and then we discovered that there was this outburst on the 10th of July, and then images on the 4th of July 2015, they were basically just showing and repeatedly showing that the cliff was standing there, while 5 days later, on the 15th of July, we can finally see that there is a bright cliff down there. So we have a pretty good feeling that it was happening at this time on 10th of July 2015. So this is an image with much higher resolution, because, you know, Rosetta, close to perihelion, has to go farther out from the comet because it was very active. So in order not to damage the spacecraft, we had to go farther out. That's why the images around perihelion are much lower resolution. But then, as the activity was decreasing, we had the possibility to return back very close to the surface. And the image right here, you don't really appreciate it, but has a resolution of less than 50 centimeter per pixel. So we are talking about a resolution per pixel close to the high-res images of Mars, so pretty important one. So this is an image of June 2016, and we basically just see that pretty big block was just falling down, and this is the result, the cliff, the new cliff that we have. So this is an image that is showing on the left side. This is a 3D model with an image stuck on top of it. And you can really see the pre-situation where there is the cliff with the layers and everything, and the cliff after the collapse. So the volume that it fell down, we are talking about dimensions of 57 meters, 65 meters, and 81 meters right here. So, and everything was falling down from a height of 134 meters. So if we compute the volume, and consider that we are computing a volume of a comet, so it's not pretty obvious, but thanks to DLR guys, we had the possibility to measure it, and we computed it, and it is around 22,000 cubic meters. So we are talking about a volume around 9 Olympic-sized swimming pools. Of course, what I was mostly interested of, because I was working on Boulder size frequency distribution and analyzing the taluses on the surface of 67P, I was mostly interested on where all these rocks were falling down and how the talus was really formed. So we had the possibility to compute the Boulder size frequency distribution for a different paper published by JB in 2016. And we had a specific size frequency distribution here. But basically, you can see that post-collapse, all the boulders, there are much more smaller boulders with respect to the big one. And this is really demonstrating that the cliff collapse was not just falling apart in 2-3 big pieces, but it was crumbling down. And while it was crumbling down, there was this outburst, because this outburst is the result of this dust that is lifted, and the volume of the dust that was lost through this outburst is around 1%, while the remaining 99% is down here. And and when we were computing the power law index of the size frequency distribution, we can really quantify that there are much more boulders with a size ranging between 1.5 to 3 meters. So what is the cause of everything? I mean, why was it collapsing, and why was it collapsing at that time? And this is a thermophysical model that was developed by Sebastian Hofner at the Max Planck Institute in Germany. And in July 2015, basically here you can really see the temperature, and the white square right here is just showing where the Aswan is, and the arrow is showing and is pointing out where the Aswan cliff is. So in 2015, the surface is basically perpendicularly illuminated for only 90 minutes during one cometary day. We are talking about one cometary day of 12.4 hours. And the surface temperature, they are rising from minus 140 Celsius to 50 degrees Celsius in less than 20 minutes. So we are talking about one thermal gradient and one surface temperature change that it was not really observed before on other bodies. And it is pretty much impressive in 20 minutes. And we also have a change of a thermal gradient of also 30 Kelvin or 30 Celsius, it's the same, per minute during when the sun is starting to shine. So what we think is that thermal cracking can really propagate into the interior of the cliff, and you gotta consider that this area was already damaged, was already fractured before the cliff collapse. So there are already fractures, and there can be the possibility that these fractures, they are just entering the cliff, and they are letting sublimation happen and erosion happen. So you gotta believe that there is this ice inside the comet, which is like gluing all together, keeping all together intact. But then all of a sudden, this glue is being loosed. So sublimation happens, then there is erosion, and then since we are talking about an overhanging cliff, this block is just freely falling down. And while it's falling down, it's crumbling apart. So why is the Aswan cliff collapse so important? Because it had the possibility to validate and had mainly 5 firsts in cometary science. The first one is that we have finally a direct link between an outburst and the crumbling material that is happening during the falling collapse, that is happening at that time. Then the second, and I would like to underline that this is a really important point because we have different ideas on how outbursts could happen on the surface of a comet. There are different reasons, but this one was one of the possibility, and we can really validate it. Then it is really exposing the pristine and the white stuff that you were seeing. It's really the pristine and fresh interior of 67P. The images that we were getting at that day, they were saturated, so we are talking about an albedo, minimum albedo. This is the lower limit, about 40%, which is pretty interesting because if you consider that the albedo of the comet ranges between 3 and 6%, it's pretty much higher. So we are seeing at a fresh interior, and we are seeing at water ices inside the comet. Then it really demonstrates this collapse that the thermal gradients, they are really fundamental drivers to the surface changes, as the model is suggesting here, which is another positive thing that we were getting. Then another plus, and I'm really in love with boulders, so it shows that how cometary talus is formed below the cliff. So how really this crumbling material is falling apart, not just, as I was saying, 2-3 pieces, 2-3 big pieces, but small dust and small chunks between 1.5 to 3 meters. And then finally, it really shows, also thanks to the other observation that Rami was showing, that comets are really some of the most geologically active bodies in the solar system. So it's pretty interesting, and this is the results that we were getting.
Just to reiterate, so the first part, all these changes are being shown in a paper in Science, while the significant events of the eclipse are in Nature Astronomy. And they'll be coming out, they should already be out, both as early release. So.
Any questions?
Do you have a hypothetical model in place for the formation mechanism of the recurring ripples?
The recurrent ripples, we think that it has to do with the geometry of the comet. So when you get a lot of activity in the northern neck, what you're having is you have gas, you have ice that is sublimating, turning into a gas, and in a sense, it's coming out with a velocity vector, the speed. In a sense, it looks like wind. It will act a little bit like wind, and we think that the peculiar geometry of the comet, because it has this concave shape at the neck, is going to funnel this gas horizontally across the neck region. And that would be the reason why you're creating the ripples specifically at that particular location. We have some models that have been published in a number of papers in 2015 that seem to suggest that, and it looks like we have visual confirmation of that indeed. So it's something that really it's one of these areas where the geometry, the complex geometry of the comet itself is playing a key role.
So it's a combination of sublimation and aeolian processes?
Yes, in a sense, yes. Well, what is happening is it's again a question of this conservation of momentum in a sense. And when you get a lot of activity specifically from the outer sides of the comet, it's losing mass. And when it's losing mass, it has to speed. When it's losing mass, especially from the extremities, it's going to speed up. And because the comet is basically at the point where it's going to be always active in these locations every time it passes, so it's going to sort of speed up. And what we've seen actually is when the activity was concentrated in the northern hemisphere early on in the mission, the comet actually slowed down a little bit from what we had measured when we first encountered the comet in August. So I think around May, it slowed down just a little bit, but then it picked up speed again and gradually increased its spin period. And by the end of the perihelion time, it had sped up by more than 7 minutes than the original value that we had when we first encountered the comet. We expect that value maybe to remain the same, more or less, as it goes through its journey and the outer reaches of the solar system, or the aphelion, because this is really a Jupiter family comet, so it's not going to go very far away. But as it comes back again in the next orbit, we expect that it picks up a little bit more speed. Now, obviously, we need to know perfectly how the comet looks on the inside. We need to know exactly what is the material strength or the material properties. And if we knew that, then in a real world, we'd be able to tell you, oh, so it's going to develop in this way, and it's going to split up at exactly that amount of time. But what we have is models and estimates. But what we're seeing so far and what the models suggest seem to be consistent, that it eventually has to speed up, and at some point when it speeds up, it will get to a limit where both bodies are going to be separated. And there have models and studies that have suggested that this is a common process on comets. And when actually they split up, it's not going to be there's not going to be a very high velocity component there, so you might end up with the lobes being separated for a while and then reconfiguring and remerging again, thus retaining the bilobe shape.
Do you have an estimate of how much mass was lost during the time period that you're looking at?
Oh, that's an interesting question. I don't think there's still anything published about that. There is a specific instrument, I think the RSI is looking at that. So I think they've already have some estimates of how much material has been lost. I don't have the number exactly in my head, but we think it's basically in the orders of meter or so that's been lost globally for the entire surface of the comet. And again, a significant thing that we're seeing here at the study is you're not losing material equally from everywhere. You're losing stuff from the south, and there's stuff that gets deposited again in the northern hemisphere, as we've seen with the dust. But also it looks like we have localized changes. So there's one particular location that I've shown where we know we've lost around 4 meters, actually, so much more than this sort of global average. But in other areas, it seems to be then less than this. So. Yeah, so that there's the redistribution component here is also a key thing, and we're learning that comets is not that simple. You're not just losing material. There's a lot of it that actually loves its home and tends to come back.
Do you have a gravity model of the comet?
Yes, of course.
Compare that to where material is moving? Gravity on a
yeah, well, we have a lot of shape models that we call shape models that we can use images to create these models. However, right now, the priority is to get really good, highly accurate shape models. So we sort of ingest all the images into the models right now. But what is really ongoing, what we're doing is now we're going to split up the imaging sequences and create shape models from before perihelion and other shape models after perihelion. And once we do that, that's actually the next step, we will be able to really compare between the two shapes. And that's also going to give us an indication of the areas where we had significant spatial changes, and maybe guide us as well to look for changes. Because at that point, these are not all the changes. We've seen more, and I've just shown you some highlights today. There's probably few, maybe even many that we're missing. We've got 80,000 images to look at. And the next step is to look at different DTMs from different time scales, and this will actually give us a lot more information, and we can be more quantitative in our estimates.
Yeah, if I can add something, you have seen with the volume computation of the Aswan cliff collapse, this was a specific point, but basically we are trying to do the same for other different areas of the surface of a comet. So the idea is having a pre and post situation and then compute the volume that was just lost and all these kind of things. So.
I have a question. So why was it that you chose 67 to investigate 67P? Was there any particular reason you chose to do that?
Oh, that's a question of history. I think the original target of Rosetta mission was Comet Virtanen.
46P.
46P Virtanen, and unfortunately we had delays in the launch of the mission, so we had to pick up a new target that would fit in with the trajectory that Space Dynamics had put for the mission, and Comet 67P fit the bill quite well. It was another one of these Jupiter family comets that had just recently entered the solar system, only in the 1950s, compared of course with something like Halley, where it's been here, it's been around this location for a long time, it's been observed by ancient civilizations. So the idea of going to 67P was again looking at a comet that has been relatively new in the inner solar system. Of course it had also an 1840 orbital configuration where it was still in the inner solar system, but it had just entered back just in the 1950s into this very close encounter due to another encounter with Jupiter. So it looked like a really valid target, and I don't think we can argue against that. It has been a pretty interesting target to look at. Yeah. I wonder what would have happened if we'd gone to Virtanen. Maybe it would have been another exciting comet, but who knows?
Yeah. Consider that Comet Virtanen, it's orbiting around the Sun, closer to the Sun for much more years than Comet 67P. So basically, we could have observed a comet that was similar to other, like Hartley or something like that. Okay, it's not hyperactive as Hartley, but it was not like pristine or new comet like 67P. So at the end, thanks to this shift in time, we were very lucky. Yeah, I'm sorry, can you say that again? Because I could not hear you.
Is there anything that you can tell from the point of, or any investigations you can do on the pristine ice that's been exposed?
Yeah. The idea is to, of course, we had these OSIRIS images. OSIRIS is a camera, is a couple of telescopes, a narrow angle camera and a wide angle camera. So, and it's observing in the visible wavelength range. There is another instrument which is called VIRTIS, and VIRTIS is a spectrometer. So basically we can go to the infrared side of the spectrum, and then we can really analyze that wool with if there are any VIRTIS cube. So I haven't really contacted them yet, but one great idea would be to interact with them and trying to see if there are the specific absorption bands of water ice and all these kind of things. One thing that we can say is that even if we are observing the visible side of the spectrum, but first of all, it is particularly bright, which is kind of difficult using other materials, you know. And the second thing is how it evolves with time. So in less than 1 year, we are going from an albedo of 40% minimum, because most likely it will be even 60% or much more, but these were the images that were saturated. Then after 6 months, in the image that I was showing you, the one with much higher resolution, the one of December 26, 2015, and that image, the albedo was already 20%. So it was a half of it. And then after 1 year, in August, basically it was 3% of the entire surface of a comet. So there is just one bright patch on the cliff that is still overhanging down there, and it has an albedo that is 80%. But this is most likely the biggest remnant of the pristine material that we had. So one idea would be to use multi-instrument analysis in order to see what was happening, also grain detection and all these kind of things. Yeah.
Any more questions? Well, thank you so much for
Thank you.
joining us today. And thank you so much for your presentations. Appreciate it. Thanks. We'll see you at the next press conference.
Thank you very much.
Thank you.